Good morning, students. So, in the last class, we started the current electricity topic and we defined about the current, average current, and instantaneous current, right? So, now today I am going to start about this current density. So, let us see about this current density. So, this current density is represented with this J or J bar. So, then current density is defined as, suppose here this current is flowing like this. In a conductor, this current is flowing in this direction like this. Now here if you are defining the current flowing through this area ds here, ds is the cross section area of that. Now current is flowing like this, and ds direction of this ds bar here, area vector. And so now the current density can be defined as this J is equal to delta I by delta T. If delta I is the current flowing through this, so if delta I is the current flowing through this, then delta I by delta S. So that means that is simply we can define it as current flowing per unit area. The current flowing per unit area is nothing but we call that as current density here. And if you want to define it a point, this is nothing but we can define like simply average current density, the average current density through the whole cross section. If you want to define it a point, so suppose if you want to define current density at any point. So at any point if you want to define, then this J we can write it as limit delta S tends to 0. That means we need to take a small point here. Here itself if you want to take like this, then we can write this as delta I by delta S under this limit, and which is nothing but we can write this as di by ds. In differential form we can write like this. Now this is a current density at any point, and this we can define it as a current density through the whole area. Current density through area ds. When you are defining current density through the whole area ds, then we define like this. If you are defining for a particular point, we define in terms of like this. And from this actually we can also define, and regarding this current density now we can observe this, the units of this current density, and clearly you can observe this di by ds simply we are writing here. So I can write this unit as ampere per meter square. Whether you are defining at a point or whether you are defining at a whole area, the current density can be defined like this. And this current density is a vector quantity, and its direction is always in the direction of this current here. This is the current direction, and this is the area vector here. For example, n cap I am taking normal to that cross section, and which is nothing but our area direction, right? This n cap is normal to this normal vector. Now the current density, if current is flowing like this, then current density will also be in the direction only. So that means, so current density is a vector, right? And its direction is in the direction of I. Then whatever the current direction, conventional current direction we are taking, so then the direction will be in the direction here. That means, so the direction of J bar is in the direction of current, right? So whatever the current direction is there, conventional current direction, so then in the same direction we consider that J vector there. So right, that means I is a scalar quantity, current itself is a scalar quantity. So to define that in vector form, we are taking this current density. So current for unit area is nothing but simply we call that as a current density there. So simply first you may write the definition, then you can copy this. The current flowing per unit area is called current density. And current density, this is the current density to the whole area, or you can call it as average current density. And if you are defining at a particular point, then we can define like this. And sometimes they will give the current density, and from that we need to find the current flowing through that conductors. So then what we can write is, so if J is current density, if J is current density, then current flowing through the cross section conductor is given by, so we can express this current as, so from this observe this, I can write this as di is equal to j into ds, and simply take this integration here. Therefore, I is equal to integral of j into ds, and actually in vector form we need to write like j bar dot ds bar. And why we are taking j bar dot ds bar means sometimes there may be case like area vector may not be in the direction of the current. Here observe this in this example, this I bar direction of the current and area both are in the same direction, right? But sometimes the situation may be different. The cross section area may be like this. So the cross section area is like this, so that this area vector will be along this direction, but the current direction is along this. So that this angle theta will exist here between this direction of the current and this area vector n cap. So then in that case what we can take is, we need to take this, now this is the direction of the j bar we can consider here. So I am representing this as a j bar, direction of the j bar, and this is the direction of the n cap. N cap is nothing but our area vector. So then in that case what we will write is integral of j into ds into cos theta we can write here, right? If there exists any such an angle theta, and limits accordingly whatever the area we want to calculate, in that area according to that limits we can take there. Like suppose if it is a cross section of radius 0 to r, then you can take the limits as from 0 to r you can consider. So that is a way of finding the current if the cross section, that means if the current density is known to us, right? If their current density and area vector both are in the same direction, then you can take directly as 0. Sometimes there may be a situations like area and this current density both are not in the same direction. There may be some angle between them, then in that case we consider like this. So that is about this current density here simply, right? So definition of this current density is simply current per unit area. I by A or I by S is called current density. So the unit will be ampere per meter square, and it is a vector quantity. Its direction is in the direction of the current, right? And next here I am going to define this drift velocity here. So in the beginning of this topic I explained like if you are taking just a conducting material, how the electrons will be in that material. So now let us consider this. So drift velocity. So just if I am taking this conducting material like this, it may be an iron rod or any conducting material, or a copper rod or any conducting metal rod, let us consider here. And we discussed already how the electrons are there inside this conducting material in the beginning of this topic. That means as we are talking about the conductor, it consists of large number of the free electrons, right? And those free electrons are not at rest. The material, that means the conductor, means it consists of the large number of free electrons, and those free electrons are traveling throughout the volume of the material randomly, and at the same time as the electrons are coming out of their parent atom, that atom will become an ion, and those ions are fixed here. That means since it is a solid, and those are called lattice ions. And so now those lattice ions are also not at rest, and we discussed already in the previous last year when you were discussing about say elasticity and expansions. We discussed that, and in heat and thermodynamics. So those materials, that solids will execute the simple harmonic motion. They are in vibratory motion. They are also not at rest, those lattice ions. And now these electrons are randomly moving throughout this volume, and they may collide with this vibrating atoms, or they may interact with their vibrating atoms, ions, vibrating ions. And so that because of that interaction or because of that collision, the direction of these electrons will be randomly changing. And so that means they are not traveling in a straight line. They are not traveling continuously in a straight line. So, right, they collide with the atom or ion and they change their direction there, and they will collide with another ion and they will change their direction, right? And so they will follow some random path here. So inside this conductor, they will follow some random path, right? So they will follow some zigzag path there. Those electrons, they may collide here and they may change the direction, and they may collide here and they may change the direction. Like this I am considering here. So they will path totally some zigzag path. And so that we discussed already, in the absence of any external field, if I am taking a cross section here, the number of electrons crossing from left to right are exactly equal to the number of electrons crossing from right to left. Got it? And so that the net charge crossing this cross section will be equal to 0. So whatever the charge is flowing from left to right, the same amount of charge is flowing in this opposite direction here. And so that net charge flowing through the cross section will be 0. And so that we say that current passing through that conductor will be 0 in the absence of any external field. Got it? And if suppose I am considering that they are traveling with some velocity, initial velocities, say u, and u1, u2, u3 be the velocity is there. And so from this what we can conclude is the average initial velocity, of electrons, free electrons in the sense, in the absence of any field. So then U average is equal to, let's suppose this is I am representing one electron, such a lot of electrons will be there and those are traveling randomly, and so that average velocity of all the electrons will be 0, right? And so I am taking them U1, U2, U3 are the velocities of those objects there, that means those electrons, plus and so on Un by N, right? Now this value is equal to 0. Got it? Because they are randomly traveling. That means those electrons U1 bar, U2 bar, U3 bar, those directions are randomly oriented such that their average will be 0. For example, if you are taking only 2 electrons are there in that material, for example, only 2 free electrons. If one electron is traveling from left to right, the other electrons should travel in opposite direction, so that the average velocity of those 2 electrons will be 0 because they are traveling in opposite direction. So like that, there are large number of electrons will be there, so that the average of all those electrons will be 0. And so then this is the U average. I am taking this as a average velocity in the absence of any external field. So that's value I am taking as equation 1. That's value. So now let us consider when you are applying some external field. When you are applying some external field, so generally suppose this zigzag path will be represented like this. Suppose I am representing this zigzag path like this. Those electrons are traveling and those electrons are reaching, for example, this point here. In the absence of one of this electron, this is the path followed by one of the electron I am considering, for example. It is starting from point A or point X and it is reaching this point Y here in the absence of any field. Now if you are applying some external field, suppose say I am applying some external field like this. An external field is applied to this material here. External electric field is applied to this material. Now because of this electric field, all the electrons will accelerate because all the electrons will experience some force, and those electrons will start accelerating opposite to the direction of electric field, that we know already, right, in electrostatics, because the electrons are negatively charged particles. So negatively charged particles will experience a force opposite to the direction of electric field, and so then force experienced by the electron will be in opposite direction, and because of this path, because of this, they will travel some additional distance than the regular distance in the absence of electric field. Suppose they are assumed to be following some path like this. So they will follow some path like this, and finally they may reach this position, say y dash. So this is nothing but actually we call the drift. That means because of this electric field, all the electrons will travel some additional distance opposite to the direction of this electric field. So now we are going to calculate the drift velocity. So let us see now what is the drift velocity there. And now let us write, first of all I am writing the data here, the force acting on the electron. So that means each electron. So this force I can write this as F is equal to, or F bar is equal to minus E into E. In vector form let us write here. You know this, and when you are writing in vector form, then F is equal to EQ. That Q value we need to substitute along with the sign. So that I am writing the negative sign there, right? And so now from this acceleration let us write here. Acceleration of each electron. So the acceleration of each electron you can write as A bar is equal to F bar by M, right? So that is the force acting on each electron. Every electron, irrespective of its direction of motion, they will experience that amount of force in the same direction, opposite the direction of electric field. Therefore, I can write this this velocity as, that means acceleration as minus E bar E into E by M, right? Capital E is the electric field applied and small e is the charge of the electron and M is the mass of the electron. Now let us write velocity of the electrons at any instant of time. Velocity of electrons after time t, right? So the velocity of electrons after time t we are writing here. So therefore this V bar is equal to, now we are writing for the different velocities, different particles. So for the different particles means I can write this as V1 bar is equal to, for one of the electron for example, then what we can write is U1 bar plus A bar into T1 bar. Now this we are writing the velocity between two successive collisions, right? That means between two collisions. It is, suppose it is making one collision here and then it is starts accelerating. Its velocity, because of that collision, its velocity decreases, it may decrease and its direction will changes, right? And but again it starts accelerating because of this electric field, right? So it makes a collision with one of the electron, one of the lattice ion. And then its velocity decreases, right? And so its velocity decreases, that but again it starts accelerating because continuously that electric field is acting. That means force due to electric field is acting. And so now if suppose if it is making another collision here. Now between these two collisions we are writing the velocity. With what velocity? Then it reaches the next lattice ion, right? So then its initial velocity we are taking as U1 and plus A1 A bar into T1. Now T1 is the time interval between, or time taken to travel from here to here, which is the time interval between collisions, two collisions. And so now it is V2 bar. Similarly for another electron, this is for one electron and this for another electron, because large number of electrons are available in this. U2 bar plus A bar into T2, right? And so on. We can write for n number of electrons. So finally Vn bar is equal to, so now this is V3 bar plus A bar into Tn, right? So that is average, that means velocities of the electrons after time t interval. That means t in the sense that t is between two successive collisions we are taking here. Here after the time t in the sense what we are considering is between two successive collisions we are taking here. And so now here now let us find average of all these values, all these velocities here. And so now that is nothing but we call that as a drift velocity here, right? So here the drift velocity is nothing but the average velocity of all the electrons in the presence of electric field. So in the absence of electric field, the average velocity is 0. That we already concluded in the beginning. Now the drift velocity is nothing but average velocity of all these electrons in the presence of electric field, external electric field. That we call the drift velocity. So you should remember, it is the average velocity of all the electrons. In some books it will be mentioned as like average velocity of one electron. So it is not true. The drift velocity is the average velocity of all the electrons in the presence of electric field. So now here, so drift velocity is average velocity of all electrons in the presence of field. In the presence of electric field. And so therefore I can write this as the drift velocity V is equal to, or let us write this, drift velocity is equal to, so we are representing now it as Vd. So Vd means our drift velocity. So this is equal to V1 bar plus V2 bar plus V3 bar plus and so on Vn bar by n, right? So then this is these V1, V2, V3 and so on Vn are given by here. So that is the velocity of the electrons after some time t, after some time, or let us write here after some time, then you will get more clarity about this. It is, we are not taking same time interval for that. After some time. After some time in the sense between the two successive collisions for that particular electron. This electron, this time is different for different electrons again. So one electron may take, suppose say 0.001 second for one collision, next collision, and another electron may take 0.004 or another electron may take 0.5, like that. Different electrons may take the different time intervals for the next collision. And so that between the two successive collisions we are writing like this. And so now let us substitute those values here. So Vd bar is equal to, I am substituting V1 bar, V2 bar, V3 bar, and I am separating them. So if you separate that, U1 bar plus U2 bar plus and so on plus Un bar by n. So all the first term here plus A bar is common for all of them, right? And then T1 plus T2 plus and so on plus Tn by n, right? So just we are substituting these values here, and all the first terms and the next second terms we are separating them, we are splitting that. So then first term you will get this, and we know already, we defined already, its value is nothing but this is the average velocity of electrons in the absence of any electric field. So in the absence of any electric field, its value is 0, right? And so then first term will be 0. So this is 0 plus A bar into, then this is taken as tau. So then here this is, we are taking from first equation here, from equation 1 we are using this average velocity we are writing as 0. So right, I will write this. And so now we are replacing the tau. The total term is replaced like this. So that means I can write this as where tau is equal to T1 plus T2 plus and so on plus Tn by n, and which we call it as relaxation time. So relaxation time. So write that relaxation time means the average time interval between two successive collisions. So here we mentioned that different electrons are taking the different time intervals here, so that we are taking T1, T2 and T3. Or the same electron may take a different time between two collisions. So for the first collision it is taking say 5 seconds for example, the next collision it may take only 1 second, or the next collision it may take 0.1 second. So like that the same electron also may take different time intervals for the next collisions. So now this relaxation time is the time interval or the average time interval between two successive collisions for all the electrons. As a whole, if you are calculating for all the electrons, the average time interval between two successive collisions is nothing but we call relaxation time, right? Here write the definition also. Relaxation time means the average time interval between two successive collisions is called relaxation time, right? And so next, let us Vd bar is equal to, now I am substituting that A value minus E into E bar into E by M into tau. So this is our drift velocity, and we write in terms of speed here. The magnitude of that velocity is nothing but our speed. So you can write this as drift speed is equal to I can write this expression as therefore this drift speed is equal to Vd is equal to E by M into tau. Now this is speed, drift speed. So this is a velocity, that negative sign is also there because these two are opposite each other. And so now there in terms of magnitude we can write this, we can write simply that drift speed as E by M into tau. So where E is the electric field, capital E is the electric field applied, external electric field applied, and small e is the charge of the electron, and tau is the relaxation time, which is average time interval between two successive collisions, and M is the mass of the electron, right? So mention those terms also. Capital E is external electric field, small e is the charge of electron, and M is the mass of electron, and tau is the relaxation time, right? So that is the expression for the drift velocity. And so now here this drift velocity is actually very small when the drift velocity is say drift velocity is of order 10 power minus 4 meter per second, and whereas the thermal velocity will be of order thermal speed of order 10 power 5 meter per second. Thermal speed in the sense which we mentioned in the absence of electric field. In the absence of electric field, we are taking like U1, U2, U3 and so on. Those velocities of order 10 power 5, and drift velocity, when you are applying external field, the drift velocity is of order 10 power minus 4. That means drift velocity is very small when compared to that of thermal velocity there. And here one theoretical question will be there. Like if you are taking in a circuit, then suppose I am taking this circuit like this. Here one electric bulb is there, and here some battery and this switch arrangement is there here. So right, suppose here this bulb is situated very far away from the source, right? And now here if suppose immediately in that circuit, if you are closing the switch here, then we know practically immediately this bulb will close here, right? But here the question is, when you are closing the switch, how the bulb will how the bulb will switch on immediately, even though the drift velocity is very small. That means the drift velocity, once if you switch on that circuit, then electric field, external electric field we are applying, and so that the velocity of electrons will fall from 10 power 5 to 10 power, here 10 power 5 will be there, but net velocity of all those electrons will be 0. That you should remember. Here with the 10 power 5 meter per second, those electrons are not traveling in the same direction. Don't confuse with those values there. So average of this value will be 0. 10 power 5 average value. That is for one electron, if you consider, it is traveling with those with that order there, 10 power 5 meter per second, right? And so now here the question is, so if you switch on that circuit, if you close the switch here, the bulb will close immediately even though the drift velocity is very low. So how it is possible? That means, for example, if I am taking some distance of 1 kilometer, the bulb is at a distance of 1 kilometer from the source, then time taken we can write it as distance by speed we should write, right? And so now once if you close the switch, then we should take it as a drift velocity. Then I can write this as 10 cubed by 10 power minus 4 for example. So it should take 10 power plus 7 seconds. It's a very large time. So right. So then that means if you close the switch, according to that, if you close the switch, the bulb should glow at the time of 10 power 7 seconds, which is not true. So practically if you close the switch, then immediately bulb will glow. So the reason for that, they will ask the reason for that. Can you explain the reason for that? So the reason is, if you close the switch here, the electrons present at the battery or electrons from the battery or electrons from the switch are not reaching the bulb to glow the bulb, right? Once if you switch on that circuit, the electric field will develop inside this conductor here, that will travels, generally the field travels with the velocity of light in vacuum, right? That means the electric field travels with the velocity of light in vacuum, 3 into 10 power 8 meter per second. That means the electric field will travels with a very high velocity, very quickly it will develop throughout this material, right? And so that the electrons present everywhere will be starts accelerating here. The electrons present near the bulb also starts accelerating there immediately if you close the switch there. So because of that, the bulb will glow immediately. That means the electrons are not traveling from battery to the bulb to switch on the bulb. So just the electric, once if you close the circuit, then electric field will develop inside the circuit immediately, because the electric field travels with a very high velocity, and so that the electric field will be developed inside that material quickly, and so that the bulb will glow there. That electric field will accelerate the electrons everywhere in that circuit, and so that bulb will glow there. So that is the reason for that, right? So the electric field will travels with a high velocity there, not because of electrons from the battery to the bulb. And next here, let us see the relation between drift velocity and the current density, which is an important relation here. Relation between drift velocity and current density. So relation between drift velocity and current density, right? And so now here the drift velocity and current density, both the formula we know or the definitions we know, just we need to write the relation. We need to combine those two relations there or the definitions. So just I am taking a conductor like this. It is connected with some external source, so that some current is flowing through it. So then let's suppose I is a current flowing through this. When I is a current flowing through this, and let's suppose say A is the area of cross section of this material here. And now here these electrons present in this material will travel in opposite direction, right? The electrons present in that material, I am representing just one electron, many electrons will be there. So those electrons will travel opposite the direction of the current. And because we know that current direction is taken as opposite the direction of flow of negatively charged particles. So when current is flowing from left to right, electrons will travel towards left. And now we are assuming all those electrons are traveling with that average velocity. So that velocity we are taking as the velocity of the electron, that is nothing but our drift velocity. And so now here in the time interval t, delta t for example, if I am considered here, the distance traveled by those electrons I am writing here. So that means first to write the consideration. Consider a conductor of cross section A. Consider a conductor of cross section A through which a current I is flowing. Through which a current I is flowing. Let Vd be the drift velocity of the electrons. Vd be the drift velocity of electrons, and n, small n, be the free electron density. Free electron density or number of charge carriers per unit volume or number of electrons, free electrons per unit volume. Number of free electrons per unit volume. So that is the meaning of this small n here, which is called free electron density, or the number of free electrons per unit volume, or the number of charge carriers per unit volume in any other material generally if you are defining there. So that means here instead of we are taking conductor means free electrons we are defining. So in general we need to define it as charge carriers. So that means instead of that free electrons we need to define it as a charge carriers for any other materials, right? And so now here in the small time interval the distance traveled by these electrons I am writing here. So like I can write this as in small time interval in the small time interval dt the distance traveled by the electrons, the distance traveled by the electron, right? So this distance we can write this as drift velocity into time. So the drift velocity into time will gives us distance. Suppose I am taking that traveling up to here, right? And so now in that let us consider the total amount of charge present in that volume. So then I can write this as total charge in the sense again total charged particles, total charge of the free electron, charge of free electrons, or those are also said to be conduction electrons, which are responsible for that conduction. So I am taking this as a dq, right? So dq is the amount of charge present on the all the free electrons we are taking there. So that I can write this as n into volume we can write, right? N is the number of charged particles present in that into volume, n into E, because we are taking that as electrons there, electrons are the charged particles here. So Ne into volume we can write, and so that I can write this as Ne into that volume of the material we can write as area of cross section into distance. The distance I can write as Vd into dt, because in the time interval, small time interval we are taking there. So finally what I can write is the charge contained in that small volume we can write as dq is equal to n into E into A into Vd into dt, right? And now from this we write that current definition here. So but therefore from this I can write this current I is equal to dq by dt you can write there. So just write the dq by dt there. Therefore I is equal to Ne into A into Vd. So this is the relation between current and drift velocity, or generally we express like this. So drift velocity Vd is equal to I by NAE. So now this is a relation between drift velocity and current. So you need to remember this relation. And in terms of current density, for example, if you are expressing. So in terms of current density, if you are expressing, then simply we know that current per unit area is nothing but we call that as current density. Therefore, but current density is equal to current density J is equal to I by A. Therefore, this Vd is equal to, I can write this as J by Ne. So that means you need to remember this relation here. The current relation between current and drift velocity. That means Vd is equal to I by NAE, right? where n is the number of electrons per unit volume, A is the cross section, and E is the charge of the electron. That means magnitude of charge of the electron, and that I is the current flowing through that, right? And so this is an important relation. And in terms of simply current density, we can write it as J by NE. So that is if you remember this equation, then in terms of current density if is required, you can write easily. So remember this equation only in terms of current only, because there will be some theoretical questions also basing on this. So VD is equal to I by NAE, right? So that is the relation here, important relation here. And so now there will be some theoretical questions basing on that. So theoretical questions basing on that means, suppose if current is conductor is of non-uniform cross section, right? So the conductor is of non-uniform cross section like this. So the electric conductor is like this here. This is area of cross section A1, and here area of cross section is A2. So clearly A2 is less than that of A1. So this value will be less than that of A1. That's we are assuming conductor is like this. Suppose here now I am taking this drift velocity as V1, and here the drift velocity is V2 I am taking here. And here suppose current flowing here is I1, then current here is I2 I am assuming here. And similarly, suppose a current density J1 here, and here current density J2 I am assuming here. So we need to write all the relations between those parameters here. So that means given condition is just by using that you can write here. So given A1 is greater than A2, right? That is a given value. And next here about the current, let us discuss first here, whether the current is constant or the current is variable. So current in the sense it's the rate of flow of charges. So that rate of flow of charges is similar to that of rate of flow of liquid in fluids. So, right? Do you remember in fluids one relation we mentioned there, which we called equation of continuity. In that equation of continuity we write A1 V1 is equal to A2 V2. And this A1 V1 is nothing but that product is nothing but dV by dt, where V is the volume. So that means now this is the rate of flow of liquid. So when the fluid is flowing through the tube of non-uniform cross section, this dV by dt value will be remains constant. Area of cross section changes, then correspondingly velocity of the fluid will adjust itself. So that but the rate of flow of fluid will remains constant. Similarly here, so when the conductor is of non-uniform cross section, the rate of flow of charges, which is nothing but current will remains constant, that is independent of the cross section area. So that means here this is mentioned that just when current is flowing through the non-uniform conductor of non-uniform cross section. We are just discussing some relations here. When current is flowing through a conductor of non-uniform cross section, conductor of non-uniform cross section, right? So we are taking such a case here. So then here what we can write is I1 is equal to I2. This will be a constant value. So remember this. I1 and I2 are, that means that I1 is equal to I2, that current is constant. Current is independent of area of cross section. Remember that. So next. So when you know this current and area of cross section, that means we know current remains constant but area of cross section is different. So from that you can answer about current density. So right. So from this current density is inversely proportional to the area of cross section. So here area of cross section is less, and so automatically their current density will be more. So J2 is greater than that of J1, because since we are writing this basing on J is inversely proportional to the area of cross section, because I is constant here, right? So next, relation between V1 and V2 we need to write, drift velocity. So then basing on this relation or basing on this relation you can answer here. So for example, if I consider here, then from this I can consider this I is constant and this N and E are already constant. They depend on the nature of the material which we are taking here. So that N value is constant for the given material, so N is constant, and E is also charge of the electron, which is a constant. And so then I is constant, we are saying that, so Vd is inversely proportional to this area of cross section. So here velocity is less means then area of cross section is less means velocity will be more. Similar to this relation here, AV is equal to constant. You can remember that equation of continuity, the similarity. So I can write this as V2 is greater than V1. Since the relation what we are taking here is basic relation, the drift velocity is inversely proportional to the area of cross section we are taking here. So those are the relations there, right? When the current is flowing through a conductor of non-uniform cross section. So next here, so let us write the relation between next J and E, electric field and the current density. So let us see about this relation between E and J. So the relation between E and J means you can write this as, so just we know already this J is equal to, we can write this as I by A, right? And so now this I value we can write this as Vd into NEA, right? So therefore you can substitute there. Therefore J is equal to Vd into Ne. Or in terms of Vd and J relation, if you take directly, you can write this relation, right? This is one relation here. Or therefore I can write this Vd is equal to, I can write this as J by Ne. So if you are taking this relation, so directly you can write this relation, or otherwise I said remember in terms of Vd and E, so I am writing like this. So let's suppose say this is equation 1. And next previously we already defined the drift velocity formula there, right? So but drift velocity is equal to, Vd is equal to, we derived a formula there. So then E by m into tau, right? So this is the second equation. So both are representing the drift velocity only. So let us combine them. So therefore from 1 and 2 I can write this as E into E by m into tau is equal to J by Ne. Therefore I can write this as E is equal to, so m by Ne square into tau into J. So now here this equation generally we are expressing it as rho into J, right? Where rho is m by Ne square into tau, and which we called resistivity. So resistivity or specific resistance. So remember this, about this we will discuss later. After the completion of Ohm's law and when we are discussing about the resistance, we will discuss more about this, right? And sometimes we express this in a reverse order, like the reciprocal of resistivity is called as conductivity. So sometimes this relation we can also express it as, or that equation can also be expressed as E into sigma is equal to J. So this I am writing this value where sigma is equal to 1 by rho, the reciprocal of resistivity, which we call conductivity. And about this resistivity and resistance, we will discuss more about this after the completion of this say Ohm's law, right? So now this is a relation here. Either we can express like this, E is equal to, this is the electric field, E is equal to, in vector form you can write here because these two are vectors, you can also write in vector form like this. So then here also I can write this E bar is equal to J bar, E bar into sigma is equal to J bar you can write. Either in this way you can express or in this way also you can express, right? And so now here there is a relation between electric field and current density there, which is a, we say microscopic relations there. And that means in a non-uniform electric field, for example, if I consider there, in case of non-uniform conductor which we discussed, sometimes they may ask the relation for the electric field, or then we need to use these equations here to calculate the electric field in such a cases, non-uniform conductors, right? And so next we need to discuss about the Ohm's law and its applications. So I will explain that Ohm's law and its applications in the next class, right? Thank you.